Okay, in section 2.9, we're going to be dealing with dimension and ranks. This is our last section of chapter 2. We've talked heavily about matrices and the role of vectors. Okay, so a little bit misleading that the title of this section is dimension and rank, and then the first thing we're actually going to talk about is going to be coordinates. Okay, so we're going to talk about the idea of a coordinate vector. So we just learned about a basis in 2.8. So given a basis, so we're going to let this cursive B be a basis for a subspace H. Okay? So B is equal to a series of vectors, or a list of vectors, V1, V2, all the way out to Vn. Okay, so I have n such vectors that make up this basis. Okay, I can establish then that any vector in H, so for any x that's in the subspace H, it has to be a linear combination of these vectors because these vectors form a basis. That's what it means to be a basis, is that they're independent and they span. So for any H, there is a vector equation. Okay, and that vector equation looks like x1, v1, plus x2, v2, all the way out to an xn, vn. Okay, where x, right, where x is equal to these weights, x1 through xn. Okay, so what we're going to talk about then is we can set this equal to any vector that's in H, like I said, equal to x. Okay, so it works for any vector in H. Now, given this information, we can set up an equation here. We can also use these weights to inform us of where a certain point is. Okay, now way back in section 1.3, we talked about some grid type diagrams. So I'm going to put one here in front of the camera from the textbook. We talked about this grid and how we have two vectors, V and V1 and V2. So there's my V1 vector, there's my V2 vector. And these form a grid here. All the multiples of V1 you see going out 2V1, 3V1, and then going out V2, 3V2. Well, I can think of this grid as representing a set of coordinates. Okay? So for example, if I take the vector -2V1 plus V2, what I'm doing is I'm taking -2V1, so 1, 2, moving on, let's call it the V1 axis. Okay, go 2 units on the V1 axis, and then up 1 along the V2 direction, or the V2 axis. Or if you prefer, I can go 1 copy of V2 out here and then go down 2 in that V1 direction. Okay, so just like we do for Cartesian coordinates, we just count the number of spaces along the grid. Okay, so we're looking then for what these coordinates are, and we can use a coordinate system based on that basis. Now, our most common basis is the identity basis. Okay, so we're going to have a basis, and this basis is going to be a basis B that consists of the following vectors: 1, 0, and 0, 1. Okay, very familiar basis to us. So then any coordinates here based on this basis, let's take the vector 6, 5. Okay, so this is V1, this is V2. 6, 5 is equal to 6 times V1 plus 5 times V2. Because I can write out what that is. That's 6 times 1, 0, plus 5 times 0, 1. Okay, and so my coordinate vector then is 6, 5. Okay, and the notation here, if I have x equal to 6, 5, the notation then is that the coordinate vector is this bracketed x. X represents my vector, and then the subscript is my basis, in this case, my basis B, which would be equal to 6, 5. So it's called the identity basis or the standard basis because the coordinate here is exactly the same pair of vectors. Okay? Now, that obviously does not have to always be the case. I can get a different basis. So let's pick a different basis. Call this B. We'll still make it a fairly simple basis. I'm going to have -1, 2 paired with 3, 1. Okay? we know that these vectors are independent because they are not multiples of each other. Remember, use all your properties that you know from before. We know they're not multiples, so we know those two vectors are independent. If there's two vectors and they're independent and they're in R2, then they must cover the whole space of R2. Okay, so I can treat these as coordinates now, and these coordinates are going to correspond to the vector. My vector x is going to equal 10, negative 3. Okay, so I know this covers all of R2, so I know this has a solution. So what I'm looking for is where x1 v1 plus x2 v2 is equal to 10, negative 3. Okay, so I'm trying to find that vector equal 10, negative 3 here. Well, as I look at this, this is exactly a vector equation. I can fill in negative 1, 2 for v1. I can fill in 3, 1 for v2, and I want to set that equal to 10, negative 3. So as I'm looking at this, this is exactly a vector equation. So what I can do to solve for x1 and x2 is just set up an augmented matrix. Okay, so I have a 2 by 3 matrix, relatively easy to deal with. 2 by 3, I can put in negative 1, 3, 10, 2, 1, negative 3. And then we're going to take the reduced row echelon form of that, and I get an ugly decimal. Okay, it does not look nice. But you can use your math fraction command here. And you see it does come out to a fraction. So 19 over 7 and 17 over 7. So this row reduces 1, 0, 0, 1 with negative 19 over 7 and 17 over 7. Okay, which means that the coordinate vector for x with respect to the basis b is equal to negative 19 over 7, positive 17 over 7. Okay, but you have to have a basis in order to do that coordinatizing or making that coordinate vector. Okay, let's look at the next one here. So I'm going to have a space H. Okay, my space H is equal to the span of two vectors, v1 and v2. Okay, and my vectors v1 and v2 are equal to 2, negative 1, 3, and v2 is equal to negative 1, 0, 4. Okay, now I only have two vectors here, but they are in R3, so they do not cover all of R3. So remember, two vectors is going to give us a plane. So we have a plane through the origin here for R3. Okay, but we're able to coordinatize this plane, even though we don't have the whole space of R3, right? With R2, we have a pretty familiar space, but maybe with slices of R3, that's going to be more difficult to deal with. So if we can have some way of representing it, that'll make it easier to handle, okay? So I'm looking for, is X an element of H? And if so, what is the coordinate vector of X with respect to the basis B? Okay, so since v1 and v2 are here, they're not multiples of each other, so they are independent. v1 and v2 are in fact a basis for H. So v1, v2 forms basis B for H. Okay, now they have to be independent, so I have independent vectors in order for it to be a basis. Okay, so now X sub B we're going to try to find. I left off the word find. We want to find at that coordinate vector. Okay, so let's consider a vector X. So our vector X is 5, negative 3, 13. So I'm looking for where x1 v1 plus x2 v2 is equal to 5, negative 3, 13. So again, I just need to augment the matrix. So 2, negative 1, 3, negative 1, 0, 4, augmented with 5, negative 3, and 13. And if this is consistent, if I get a consistent system, then I know that X is in the space H. Okay? So we're going to go to our matrix. We're going to do a 3 by 3 matrix. Going across, I've got 2, -1, 5. -1, 0, and -3. 3, 4, and 13. Okay. And we were going to do a RREF. Remember, go to math, go to RREF, matrix A, where I stored it or wherever you stored it. We get that result 1, 0, 3, and 0, 1, 1. Okay. So this reduces to 1, 0, 3, and 0, 1, 1. Remember, this is augmented. So this tells us then that x1 is equal to 3 and x2 is equal to 1. Okay, so it's consistent. So yes, x is in H. And my coordinate vector with respect to the basis B has only 2 inputs in it, 3 and 1. Okay, because I have only 2 vectors in my basis. So even though my vectors here are in R3, this forms a plane. Planes are 2-dimensional, so my coordinate vector has just 2 coordinates. Okay? Now, there is not just one basis. Certainly, as we've seen in R2, R2 could have many bases. I already showed you 2 such examples, the standard basis and then a different basis that I gave there. Okay, so a vector can be the same vector in with each basis, but have different coordinates depending on the basis. Okay, so let's look at 2 separate bases here in our next example. So I'm going to have basis B is equal to B1, B2. Sorry, let me get my camera to cooperate there. Okay, my B1 vector is going to be 3, 1. And my B2 vector is going to be -1, 2. Okay, then I'm going to have a basis C that's made up of vectors C1 and C2. My C1 vector is going to be 6, 1. And my C2 vector is going to be -4, -3. Okay, so as I look at these are both clearly bases. I have 2 vectors. They are not multiples of each other. I can't multiply something by this one B1 and get B2. I can't do the same thing for C. So these are clearly bases. They're bases for all of R2 because they line up. Those dimensions, there's that word that we're going to talk about in this section a lot. Those dimensions match, right? R2 has 2 ways to go. Think of it as up, down, and left, right. You know, we don't have a third dimension. And if I have 2 vectors, then that covers the whole space. R3, I would need 3 vectors. R4, I would need 4 vectors. Okay? So it's clear, these are clearly bases. So I need to find now a coordinate vector x with respect to the basis B and another coordinate vector with respect to the basis C when my x vector is equal to 14, 0. Okay? So I have 2 different setups here. First, I have my basis B. That's 3, 1 for the first column. Second column is -1, 2, augmenting it with 14, 0. Okay, so this is for B. Now for the basis C, I've got 6, 1 first column, -4, -3 in the second column, and then still augmenting it with 14, 0. Okay, and we're going to row reduce each of these. Now, I know that I'm going to get the identity because I know that it's a basis. So I know they're independent. I just have to figure out how I need to line them up. Okay? Use your calculator. The other thing you can do is you can go through here and say, okay, what do I need to multiply here? You can do some guess and check work. Well, if I do 3, I got to get it up to 14. So what about 3 times 4? Okay, that's 12. Then I would need 2 more to get to 14. So 12 and 2. Well, let's try for a candidate here. Let's try 4 and -2. Okay, 4 times 3 is 12. -2 times -1 is 2. 12 and 2 make 14. 4 times 1 is 4. And 2 times -2 is -4. I get 0. So that does work. That's 4 and -2. You can always do the row operations, okay? Nothing wrong with doing the row operations. Row operations are good. But you should get 4, -2. Then let's check it over here. Am I guaranteed to get 4 and negative 2? Well, no, I have a different matrix here. I have a totally different basis that I'm trying to add up. So again, I'm trying to get it up to 14. So how about 3? Well, 3 times 6 gets me 18. Minus 4 would be 14. So my candidate here I'm thinking about then is 3, 1. And sure enough, that will work for the bottom row too. 3 times 1 is 3, and minus 3 gets me 0. So 3, 1 works there. So my coordinate vectors, xb, was 4, negative 2, where my coordinate vector xc is 3, 1. Okay? No reason to think these are the same, even though x in both cases is the same. So if we graph the point 14, 0, it doesn't move. But how I count to get there just changes. It's just taking a different path around the grid. So think about that grid that I showed earlier in the lesson with 1.3. There are multiple paths you can take to get to that same point, but either way, you wind up at the same spot. Okay? So look at that picture, right? Perhaps to get to V2, I just decided to go straight up and straight over. That's going to get me a different basis, a different coordinate vector than just going out on the V2 axis, let's call it. Okay? So I have those relationships then for coordinate vectors. Okay, now the section was called dimension and rank, so we need to talk about dimension and rank. Okay? We've talked a lot about bases at this point. Okay? So the dimension of a subspace, can't spell, sorry, is the number of vectors in a basis for the subspace. Okay, the dimension of a subspace is the number of vectors in a basis for the subspace. Okay, so if R2, 2 vectors in the basis, dimension is 2. Okay, think about the one we did with the R3 vectors, right? I had these two, V1 and V2 here. Okay, they're independent, so I have 2 vectors in that basis. They form a subspace with dimension 2. So it's purely the number of vectors in the basis. There's one exception, except if the space is just the 0 vector. Okay, the 0 vector has dimension 0. Okay, so if you just have the 0 vector, you have dimension 0, even though there is one vector in that space, the 0 vector. Okay, but we say that has dimension 0 so that we don't mix it up with the cases where I really do have a span that makes a line. Okay, so a dimension is the number of vectors in a basis. Okay. All right, now it's the name of the section is dimension and rank, so we need a definition for rank. So the rank of a matrix is the dimension of the column space. So we talked about column spaces in the last section. Okay, so simply written, that's rank A, and we don't abbreviate rank at all. We just say rank A is equal to the dimension, which we do abbreviate DIM or dim, the column space of A. Okay, so the rank of a matrix is the dimension, and that looks like an N, the dimension of the column space. Okay, so let's take a look at a matrix and let's make some observations about it. Okay, based on what we learned in 2.8 and now our new definitions. Okay, so I have a matrix A here. My matrix A is 3, 6, negative 1, 1, negative 7. And I have 1, negative 2, 2, 3, negative 1, 2, negative 4, 5, 8, and negative 4. Okay. Now I'm going to tell you what a reduced version of that matrix is. A reduced version of that matrix looks like 1, negative 2, 0, negative 1, and 3. 0, 0, 1, 2, and -2, and then all zeros for the bottom row. Okay, so I have this matrix, I have its reduced form. Now remember what we learned about column space. We learned that the column space is all the linear combinations of the columns. So I need to identify which columns are independent. In this case, that's where the pivots are. So I have pivots in the first and third columns. Okay, that means that the column space, so col A, is equal to the span of the corresponding vectors. Okay, remember, don't take them from the reduced matrix, take them from the original. But 1 and 3 are my pivot columns. So my first vector, 3, 1, 2, and my second vector, -1, 2, 5. Okay, they make up the column space. The span of them does. There are two vectors here. They're clearly independent. They don't have any multiples of each other. I got the identities when I did the row operation, so I know they're independent that way as well. So those two vectors are linearly independent. Thus, I know that the column space then, or I'm sorry, we know that that's a basis. So I have a basis with two vectors in it. So the dimension of the column space of A is 2. Now, I can also talk about the null space while I'm here. So the null space, remember, we find by solving AX equals 0. Okay, so AX equals 0 would have the solution set x1 is equal to 2x2. Again, remember, you take this to the other side of the equal sign, plus x4 minus 3x5. Again, moving each of those to the other side of the equal sign. x2 is a free variable, so x2 is x2. x3, again, you're taking this to the other side of the equal sign, so you get negative 2x4 plus 2x5. x4 is a free variable, and x5 is a free variable. Okay, notice those are not pivot columns, so they must be free variables. So I can write those in vector form then. So for x4, my vector is, I'm sorry, for x2, my vector is 2, 1, 0, 0, and 0. Again, just reading off the coefficients, 2, 1, then I have no copies of x2 in the last three. Second one then is going to be x4. I have 1, 0, -2, 1, and 0. Again, reading the coefficients, 1, no copies of x4 here, -2, 1, and no copies there. And then the third column, -3, 0, 2, 0, and 1. Okay, it's common for students to leave off the 1 relating to the free variable here. So that 1 for x5 gets left off, or the 1 here for x4 gets left off. Okay, so the span of these three vectors is the null space. Okay, these three vectors are linearly independent. If they're independent, then they form a basis for this space. So notice here that the dimension of the null space is equal to 3 because I have three vectors. Okay, it is not coincidence then that the dimension of the column space 2 and the dimension of the null space 3 add up to the number of columns I have here, or the number of vectors I start with, 5. Okay, that's going to be an important theorem that we're going to see again here in just a bit. Okay. So I have two theorems here. They're called the rank theorem and the basis theorem. Okay. So the rank theorem says that, I'll go to a new page here at the bottom of that one. Our theorem says the rank theorem if matrix A has n columns, which is normal, right? We typically write a matrix as m by n. Then the rank of A plus the dimension of the null space is equal to that number of columns n. And remember that the rank of A can be written as the dimension of the column space. Okay? But notice that these are not subsets of the same place, right? So if you look back at our last example, right, the column space was in R3 because these have 3 coordinates to them, 3 positions, 3 entries. Where my null space was in R5. Okay? We have to have that matching setup in order to keep that straight. We have to make sure that we're talking about the same pieces of the same spaces. Okay? So that's our rank theorem. Okay? So let's use that here in a matrix A. So I've got a matrix A. This matrix is a pretty big matrix, but I'm going to give you the tools here. 2, 4, 6, 0. Second column then is 5, 7, 9, -9. Third column is -3, -4, -5, and 6. Fourth column, -4, -3, 2, and 5. Fifth column and last column, 8, 9, 4, and -6. So we've got a big, ugly matrix here to deal with. I'm going to go ahead and give you a echelon form of it, not a reduced echelon form, but an echelon form. So 2, 5, -3, -4, 8 along the top row. Second row is going to be 0, -3, 2, 5, and -7. Fourth row is going to be 0, 0, 0, 4, and 6, -6, sorry. And then the fourth row is going to be all zeros. Okay? So from this echelon form, I can already identify the pivots, right? I have a pivot there, pivot here, and a pivot here. 3 pivots. Now from that, I can already ascertain the column space. I know that the column space then is going to be those 3 columns. Okay, 1, 2, and 4. Now to get the null space, I would have to get this to reduced echelon form. But I know from my rank theorem, okay, so I have then that the rank of A is 3 because the column space is going to have 3 vectors in its basis. From the rank theorem, then, I know that the dimension of the null space must be 2. And notice that is also equal to the number of free variables I would have in the homogeneous system. Okay, so we have all those tools at our disposal. Now, it's important that we match up the dimension matching here, okay? And so that is our basis theorem. Okay? Our basis theorem says that if I have H is a p-dimensional subspace of Rn. So H is a p-dimensional subspace of Rn. Any linearly independent set of exactly p elements is automatically a basis for H. Okay, so if I have 3 vectors, v1, v2, and v3, independent in R3, I have 3 vectors in R3, so then v1, v2, v3 is a basis for R3. Okay? But notice that I've got to get the dimensions to line up. If these are vectors in R4, then these are a basis, but they're not a basis for R4 because I don't have enough of them. Okay, I have to get those to line up appropriately in order to cover that whole space. Okay, If you don't have enough vectors, you can't cover the entire space. So make sure you're paying careful attention to that. Okay. Now, given our new definitions, we can add to our invertible matrix theorem. So remember our invertible matrix theorem, we had all these 12 properties, A through L. Okay, go back and check our video in 2.3 if you need to hear more about those again. Okay, that was in 2.3. We're going to add to that invertible matrix theorem. So that was A through L. So our invertible matrix theorem here is going to pick up with M. So these statements are equivalent, just like the others, okay? Well, if the columns of your matrix form a basis for Rn, in other words, they're independent, that means it's invertible, okay? It ties it back together. Basis, independent, invertible. If the column space of A is all of Rn, that means that A is a basis, which means the vectors are independent, which means it's invertible, okay? If the dimension of the column space is n, that means you have n vectors, which by the basis theorem tells us n independent vectors. The column space is the whole thing. That means it's a basis. That means they're independent. It means it's invertible. It all ties together. Dimension of the column space is exactly the rank. So O and P are almost exactly the same theorem because that's just the definition of the rank. If the rank is the whole matrix, the whole space, the column space is everybody, there's nobody left for the null space. So the null space of A being 0 means that the homogeneous equation has only the trivial solution. And if the dimension of the null space is 0, that accomplishes the same thing because the only space with a dimension 0 is just the 0 vector. So we can tack all of those properties on to our invertible matrix theorem. So we've broadened our invertible matrix theorem all the way out to statement R. So we're up to 18 statements in our invertible matrix theorem. Okay. All right, so you can find all that out using the tools that are given there, the properties, okay? But it's important that you make sure you know what space each of these lie in, right? So if you've got a 3 by 5 matrix, for example, okay, like one we did, we had 3 by 5. The column space is in R3, but the null space would be in R5, okay? And so take any matrix that you've got, whatever size you make it. Say I have a 7 by 5 matrix, okay? So the column space, so A is a 7 by 5 matrix. Column of A is in R7. It's not all of R7 because there's only 5 vectors to choose from. Okay? The null space is in R5. Okay? So the column space is always in Rm, number of rows. The null space is always in Rn, the number of columns. Okay? Now let's say I know something about this A. This 7 by 5 matrix has 3 pivots. Well, if there's 3 pivots, I have 3 independent columns. So the rank of A would equal 3. 3 independent columns. Column space has 3 vectors in its basis. Dimension of the column space is the rank. Tie it all together. 3 pivots gets us that. Now, I have 5 total possibilities. I have 5 variables. 3 of them are basic variables based on the rank. That leaves 2 left over by the rank theorem or the rank nullity theorem. Hey, that's just another name for it. You can just call it the rank theorem. Nothing to worry about there. Which means that the dimension of the null space is equal to 5 minus 3. The dimension of the null space is 2, which also tells me that AX equals 0 has 2 free variables. Okay, it tells me all of that. I can tie all of that back together using that as theorems. Okay, so use your number of pivots, use your rank theorem, use the properties of column space and null space to match up your dimensions appropriately. Okay, so that's the end of section 2.9, and that's the end of chapter 2. Okay, so check through your various syllabi and checklists and course setups and make sure that you are prepared for any quizzes, tests that come up here at the end of chapter 2. Okay, please contact me if there's any help I can provide. any questions you have, and I'm happy to assist. And I will talk to you next time when we start chapter 3 about determinants. Okay, we've talked a little bit about determinants already, but we're going to broaden those definitions for some bigger systems and some different properties we get from determinants. Okay, all right, see you for chapter 3.